talk about water. The book likes to point this out. They call the water a proxy for life. You may have wondered why you keep hearing, oh, scientists think there may be water on Mars in this spot, or maybe in this spot. The reason they're so worked up about that is that we have never found life without water. And yes, I know about tardigrades. Don't try to stop me about tardigrades. Even they have some water. We don't think we'll probably find life where there's no water. We're very interested in where there's liquid water in the universe, because we think that's where life might be. And the reason why is that all the chemical reactions that we know of take place in water. Water is a polar molecule. The reason why is because oxygen hogs electrons. Oxygen is very electronegative. Water has an oxygen and two hydrogens with a bend. And because oxygen hogs the electrons, it's a little bit negative on this side of the molecule. And because hydrogen doesn't get the electrons, it's a little bit positive on this side of the molecule. What that means is you can form these dotted lines. What do we call the dotted lines? Oh, sorry, what do we call? Yeah, the hydrogen bonds, you were right. We have these dotted lines. What that means is the little bit of negative charge of this oxygen, it's attracted a little bit positive on that hydrogen of that other molecule. And so all the molecules are kind of hooked together. If you get nothing else out of this class, you can, when your 5-year-old nephew asks you, Uncle Joey, why is water wet? You can answer that now. Well, the reason that it feels wet, when you're putting your hand in, you are pushing apart weak hydrogen bonds. That's what you're doing. The wet you're feeling is the breaking of the hydrogen bonds. Water has this bend in it, and that allows it to have a negative end and a positive end, so it's polar like a magnet. You know, magnet has a negative end and a positive end. Unless things hook together, you're fine with this, right? It sounds like what we just said. We form all these hydrogen bonds that hold everything together, and it's fine. Because water is polar, it's really good at dissolving other polar molecules. Let's talk about solutions. Remember, the whole point here is that water is good at dissolving stuff, right? Well, in reality, water is not good at dissolving everything. Water is good at dissolving everything that is a polar molecule. Or I should say things that have a charge. If they have a charge, you can dissolve them. Now, we have to talk about solutions, and everybody comes up with complicated ways to explain solutions. It's simple. A solution is what you drink. It's the Kool-Aid drink. Okay? The solute is the stuff you want to dissolve, like the Kool-Aid powder and the sugar. Okay? Easy. The solvent is the stuff that you dissolve things in, like water. Water is a good solvent. A lot of people like to say it is the universal solvent. It is not the universal solvent, it's just really good. The reason that water is a good solvent, not a universal solvent, you have people saying that, it can't dissolve things that are not polar. Things that are not polar are hydrophobic. Remember we're talking about the awesomeness of phospholipids? Those tails, they don't want to be near the water. Oil doesn't want to be near the water. Those things are hydrophobic. Why are they hydrophobic? Because they are not polar. Water is good at dissolving polar things. I would recommend watching the Properties of Water, Water is Liquid Awesome, Hank Green video that you have a link to there, or you have a link on SlothNet. You're going to watch it, right? Right? Properties of water, most biological substances, not the lipids, dissolve in water. Everybody calls it a universal solvent. In reality, it's a nearly universal solvent because there's some things that don't dissolve well. But it's really good dissolving anything with a charge on it. So let's look at sodium chloride, right? Table salt. Throw that into water, stir it up, and it dissolves. Nobody's surprised by that. You've done this before. Water is forming hydration shells. It's a shell of water. How do you physically separate this sodium? And it's a sodium ion. It's already lost its electrons, so we don't have to worry about it causing mayhem, right? That's what we were worried about before was when you put sodium there with one on the outer layer, it wants to react violently. Well, it's already lost that one. You see that, right? All right. But how do we dissolve it? Well, this has a positive charge. So the negative oxygens line up, slightly negative oxygens line up facing it. They form a shell, and they keep it away from the chlorine. The chlorine has a slightly negative charge because it picked up. So all of the positively charged hydrogens line up next to it. In both cases, we have a shell made out of water, a hydration shell. How do we put these back together? Suppose we want to make it back into table salt, like that. How do you do that? Yeah, you dehydrate the water. If you let enough of water evaporate off that you don't have enough water to make shells anymore, you got salt again. But hydration shells are really good at dissolving things. Water is good at dissolving anything with a charge. Water dissolves polar molecules and substances that have ionic bonds. You get these fairly strong bonds between the ions. You understand that we already did what ions are. You know this happens because you swap electrons. And water is good at dissolving anything that did that because there's a charge. Properties of water. Water has cohesion. That means the water molecules stick together. You've seen this. There's like this skin on the top of the water, the surface tension. If you were me, the bad kid when you were small, you used to take drinks when you're waiting at the pizza parlor, and you would add water as much as you could until you had it way over the top of the glass and see how high you could go. And then, of course, someone would vibrate the table, and the skin would break, and the water tension would break, and you make a mess. And then the waitress would give you that horrible, dirty look. I was that child. But you know what I'm talking about, right? Right? That's
like a little.
Yes.
I've done it with the penny.
Yes.
Little drops.
Exactly. And the reason it happens is because the water molecules on the surface are sticking to each other. They form that skin, right? They call that surface tension. That's caused by cohesion. Cohesion is the word we use when water molecules want to cling together. This is important in moving fluid through things like plant vessels, because like if you move one water molecule, it holds on to the one next to it and moves that one too, and moves that one, the next one down, the next one down. Adhesion is water sticking to other stuff. And this is a big deal because it's also used in, if you have a really narrow vessel, then the water kind of climbs the side of it. That's the reason why. So again, if you're dealing with a very narrow tube in a plant or in a cell, that narrow tube, the water is going to crawl along the side because it's sticking to the side. Large liquid range. This is a big deal. This is, by the way, every single thing that's listed right here is caused by hydrogen bonds. Okay? Cohesion. Why? The molecules are sticking to each other because they're hydrogen bonds. Adhesion, they stick to the things around them, at least if they're polar, from hydrogen bonds. The large liquid range, this is pretty simple, but it's because of hydrogen bonds. You would agree, we've got a lot of hydrogen bonds going on. One molecule can be loosely held to a lot of other water molecules. Say we wanted to turn this water molecule into gas. To do that, we have to break this hydrogen, come back mouse, this hydrogen bond, and this hydrogen bond, and this hydrogen bond, and this hydrogen bond. We have to break all those bonds to turn this into gas. So it takes a lot of energy, a lot of heat. That's why there's a big range over which water can be liquid. Solid water, less dense than liquid. This is special, this is weird. Very few things do this. Now you can see the reason why. Liquid water, you've got those hydrogen bonds, but it still can move around, and the molecules can get kind of close to each other. That's ice. Molecules are spread out. See the difference? If they're spread out, you have fewer molecules in one spot. So it's less dense. Here you can pack them closer, it's more dense. You're like, yeah, so what? This is why this matters for life. I'm going to draw a lake. We've got a lake. We got water in the lake. And we've got a fish in the lake. Now, let's suppose we're not here in Florida. Let's suppose we're up in Michigan. I went to school in Michigan. What happens in the lake in Michigan in the winter? It freezes. So, do you know why? Because the air gets cold. When the air gets cold, it's exposed to the water. The water gets cold. When that happens, the water gets denser and it starts to drop. And that causes the warmer water here to go up by the surface, and it's cooled down too. And then, so you get this cycle until everything gets cool. And you're like, oh no, it's going to get cold and freeze solid, and then the fish will die. That's not what happens. If you get the water cold enough, it starts going the opposite direction. It starts forming very organized bonds, spreading apart and getting less dense. So what happens then, instead of the water cycling, is air gets the water cold, water stays there at the surface. Gets cold in this layer. Gets colder, gets less dense, colder, less dense, colder, less dense, until it forms a solid layer across the top. We've now got a cap of ice. And underneath the water is a little bit warmer. And fish is happy about this. Does that make sense? All right. Most substances don't do that. If you take a metal and you cool it down, it gets more dense. And you cool it down, it gets more dense. And you cool it down, it gets more dense. And that's what it does. Water will reverse, and partway through that cycle, it'll start getting less dense. That lets you freeze things, but not freeze them solid. Keep it liquid underneath. This matters. This matters a lot for life. Yes?
Is water the only thing that will do that?
The only thing I know of, but there may be other things that chemists would know of. Europa Report is a sci-fi movie about going to the moon Europa, moon of Jupiter, looking for life. And actually NASA has been talking about going there to look for life. Our little generator to make the nose really hot and melt its way a mile down and then swim around underneath looking for things. But the reason Europa matters is water. We think it may have liquid water, so we're very interested in it. Properties of water. Water will very briefly split apart into hydrogen and hydroxide and join back together. And that matters a lot. If you hear someone talk about pH, they're talking about how much hydrogen is in the thing. pH is the concentration of hydrogen ions. If we say that something is acid, that means it has more hydrogens than hydroxides. If we say something's basic, that means it has more hydroxides than hydrogens. If you're looking at like Drano, it's almost all hydroxide. So it's very basic. If you're looking at battery acid in your car's battery, you know that's acidic because it's called battery acid. Well, what that means is it's full of hydrogen ions. Almost no hydroxides. I need you to memorize this. I'm telling you right now, I know it's a little complicated, I know it's a little weird. pH is the concentration of hydrogen ions. The lower the pH, the more acidic it is. The lower the pH, the more hydrogen ions. If you really need to know why, it's because there's a negative logarithmic scale, but we're leaving the math out, okay? But just memorize that low numbers are very acidic, high numbers are very basic. Right here in the middle at 7, you can see you have an equal number of hydrogen and hydroxide ions. 7 is neutral. Your blood plasma is 7.35 to 7.45, right in there. So acids have lots of hydrogens and their pH is a low number, closer to 0. Bases have very few hydrogens and their pH is closer to 14. Let's talk about buffers. There's this experiment they do over in anatomy, it's pretty cool. They take a little vial of water and a little vial of blood plasma, and they look basically the same. There's a little bit of a light yellow straw colored blood plasma, and they're basically the same thing. And they check their pH, and they're both right around 7. They add acid to both of them, and the water pH drops. The blood plasma pH stays right around 7. And they add a little more acid to both, and the water pH drops some more, and the blood pH stays about the same. And they add a little more acid, and the water pH drops a little more, and the blood plasma pH drops down. The reason why is because the blood plasma has a chemical called a buffer. Buffers can resist changes in pH. They can stop it from getting too acidic or too basic. They can't flat out prevent it from ever happening. You can put in too much acid and overwhelm the buffer. That's what they do in that demonstration. Blood plasma has this going on all the time. You would agree that blood has water in it. You'd agree that you're breathing out carbon dioxide, right? Right? So when your cells make carbon dioxide, they put it in the blood. And you carry that off to your lungs and breathe it out. Well, what that means is that you have, for a while in the body, water hanging out with carbon dioxide. It joins up to form carbonic acid. And why do we call it an acid? Because anything that can break down and give off a free hydrogen is an acid. Good, so carbonic acid is an acid. But that means you have this bicarbonate floating around too. Bicarbonate buffering system. The blood plasma has a bicarbonate buffer. If I add acid, if I add hydrogen ions to the blood plasma, the bicarbonate in the blood plasma will pick up the hydrogen ions. And so it's like they're not there anymore. And so that stops it from registering as acidic. Are you with me? Does that make sense? Yep. Okay. When we talked about buffers, you would agree that a buffer reduces the tendency of the pH to go up or down, yes? True. You understand the method. Either absorbs or releases hydrogen as needed. Good? Yes. The book goes on with this thing at the end about weird life. Is it alive? Well, I'm going to answer the question for you because we have our 6 properties of life. No, viruses, not alive. No, prions, not alive. Hey, have we talked about what prions are?
No.
Okay, well, we need to talk about prions real quick because we're almost at the end of this, but prions you need to know. If you watch Star Trek, not that series, but if you watch Next Gen, there are these big bad things they have to fight against called the Borg. The Borg are humanoid, they're kind of humanish. But they are all jacked up with all kinds of electronics. If you're captured by the Borg, or if you're fighting the Borg, they'll yell, "Resistance is futile, you will be assimilated!" And they will capture you. And then they will do things like rip out your eyeball and replace it with an infrared camera so you can see to fight at night. But they'll also jack all these things into your brain so you can't think by yourself. You're part of the collective hive mind. You know what I'm talking about, right? Right? Okay, those are the Borg. Well, prions are Borg proteins, and I mean that really. You may have heard of a few of them. You have this version, and then you have 2 versions of this protein. This version is the normal version of the protein. Now, you've heard of the disease caused by this. If you hunt, you might have heard of chronic wasting disorder in deer, and you're a little bit of a nod there. You know what I'm talking about? If you shoot a deer in some parts of the country, they don't want you to just go and dress it out, or they don't want you to go and take it to someone and have it dressed. They want you to have the spinal column of the brain tested to make sure it's safe to eat. In sheep, they call this scrapies. In cows, you've probably heard of mad cow disease. When humans get infected by it, that's Crutchfield-Jacobs. In humans, they call this disease Crutchfield-Jacobs. They're prions, okay? Normal shaped protein. Now, if you change the shape of a protein, does it work anymore?
No.
No. And prions are proteinaceous infectious particles. You might as well write it down. It's P-R-I-O-N, prion. Okay? Proteinaceous infectious particles. They're not a thing that's alive, they're just a protein. But they change shape. From this shape that's kind of spread out, if this one, this Borg protein, this prion, touches this one, it'll take up the same shape. And what happens is then this one, the next one it touches, it'll change shape. And the next one, it'll change shape. They'll keep converting every other normal protein they touch to be like them, change into their shape. And it's a little more compact shape. Anybody know the real name for mad cow disease, the sciencey way of saying it? Bovine spongiform encephalitis, encephalopathy. What that means is it infects cows and it makes their brain, it inflames their brain, and it makes it sponge-like. It makes holes in the brain. How do you make holes in the brain? Well, you take all these things that are spread out and you gather them up. That's where you get your holes from. Does that make sense? And they don't do their job anymore, insulating the cells, and so you can't send nerve signals, and oh wow, you're screwed. Are they alive or are they not? Well, I don't know why they're making it complicated. No, it's a protein. It's not a living thing. It's just a protein. Okay? No, it's a virus. It's not a protein. Yes, weird bacteria are still bacteria. They're still alive. They still do all the things. They reproduce themselves. Archaea that live in weird places like the bottom of the ocean, the hot sea vent, they're still alive. They're still fully alive. So the way that we're going to define life in this class is the way most books do. We're going to avoid that weird life thing the book does. If it meets all 6 criteria, it's alive. If it doesn't, it's not. It might be right on the edge. A lot of people like to argue whether a virus is something that was alive and it's lost some of the functionality, or maybe something about to become alive. Well, great question. Lots of fun. You can write some good sci-fi stories about it, but it really doesn't affect the fact that it doesn't meet all 6 criteria, so it's not alive. Good? All right. So, in summary, would you agree that organisms grow, reproduce, maintain homeostasis by taking in energy from the environment? What are the 2 big broad categories for taking in the energy for homeostasis? A word?
Autotrophs and heterotrophs.
Yep, autotrophs and heterotrophs. Hey, what's the most common type of autotrophy on this planet?
Photosynthesis.
Photosynthesis, exactly. What's the one you have in deep sea vents and places with no light?
Chemosynthesis.
Chemosynthesis. You guys are good. That's okay. I've been bitten. Ow, he has teeth. Ow, ow, ow.